All right, so his next speak will be by Ingrid Vazquez-Holm, and she will tell us about loop level double copy for massive quantum particles. Please go ahead.
Thank you. So first of all, thank you so much for inviting me to give this talk. I'm really excited and a little bit nervous to be talking, but hopefully it'll be fine. Today I'll be talking about loop level double copy for massive quantum particles, which is based on projects I've had with my advisor, JJ. And basically what we've tried to do is we've tried to find this color kinematics satisfying representation for amplitudes from massive scalars at both tree and loop level. And of course, a strong motivation to do this is that if we find a color kinematics satisfying representation, we can take the double copy and find the gravitational amplitudes. So why is it hard to do gravity with traditional methods? I'm sure this is not new to a lot of people here, but two of the challenges are that if we use off-shelf Feynman rules, we often get very large and unwieldy expressions, even though the resulting amplitudes are actually quite compact. In addition, the fact that gravity couples to itself means that as we go up in multiplicity and loop level, the number of graphs that contribute just explode factorially. So we've come up with a bootstrapping method that tries to remedy these two challenges. And the first thing we exploit is the color kinematics duality. And this allows us to relate the kinematic information in different graphs and write them in terms of a much smaller basis of graphs. And in addition, we use unitarity methods, so factorization at tree level and unitarity cuts at loop level, which allows us to write our expressions in terms of on-shell expressions, which are smaller and more compact. So before I dive into this, I just want to state a few things that we did find about this representation. And we find that there is a color kinematics satisfying representation for amplitudes at tree level, and these are completely determined by color kinematics and their factorization properties. And in fact, we can also find a color dual representation for loop level amplitudes, and these are completely determined also by color kinematics and generalized unitarity cuts. And finally, these representations that we find can be used to describe massive scalars charged in both the fundamental and the adjoint representation of the gauge group. So I think we got a very nice introduction, or we got a few nice introductions to color kinematics yesterday. So I'll try to introduce it from a very graph-based point of view. And then I'll go through our bootstrapping method at tree level, then the bootstrapping at loop level, and at the end, I'll see how we can actually extract some gravity amplitudes from these results. So let's start with the color kinematics duality. Now, a color dual representation means that we find a representation where the kinematic weights of graphs obey the same algebraic relations as the color weights. And this means that we can write our kinematic information in terms of a smaller set of basis graphs. And once we have something in this representation, we can combine the numerators and double copy them and get amplitudes in new theories. So this gives us a kind of web of theories where we can reach different amplitudes. Now, initially, the color kinematics duality was established for massless particles in the adjoint, but now it exists for all sorts of particles in all sorts of representations. So today I'll be focusing on massive matter charged in the fundamental. So let's start with just the general expression of an L-loop amplitude. What we see is that we sum over the graphs that contribute, and each graph gets stressed with this fraction. And this fraction is the part that I want to focus on now. So I'll start with the massless case, and then we'll get to the massless later. So we'll just take as an example the 4-point gluon amplitude. And the color factor for this guy is relatively easy to read off. You just take the structure functions and dress the vertices with them. Now, this color factor obeys the Jacobi relationship, which we can show graphically in this way. The kinematic numerator is a little bit harder to read off the graph. It's not as clear what it's going to be. And this is, in fact, the functions that we want to determine in this project. So we're going to treat them as numerator functions. So each distinct topology gets its own numerator function. And the arguments of this function are the external legs, so in this case, the ordered external legs. So what we want to impose is that these numerator functions obey the same type of relationship as the color factors. And you see that since these are all the same topology, they get the same numerator function, but with different arguments. In addition, these structure constants have an anti-symmetry that if you flip two of the legs, so if we take this 3-point vertex, if we flip A and B, we get a minus sign. And similarly, we want our kinematic numerators to have the same anti-symmetry property. Now, of course, I've only shown you this for a 4-point example, in which case it seems very straightforward. But we want this to be true for all graphs. So if we take some m-point graph and we look at one of the internal edges, we can think of this as a Mandelstam S channel. Now, if we change the connectivity to a T channel and a U channel, then we want these three graphs to obey this same relationship. Now, this was the massless case and probably quite familiar to a lot of people here, but we of course want to introduce mass into our amplitudes. And we do that using this vertex where we have two massive scalars coupled to a gluon. And this gets dressed with a generator. So how we dress this at this point depends on whether we treat this as a fundamental type particle or an adjoint type particle. Now, if we treat it as a fundamental type particle, we're going to get a sort of a direction for this line. We're going to get a particle and an antiparticle. And we can see this as an I and a J bar. However, if we treat this as an adjoint type particle, this is more like a real scalar where we don't really have a particle-antiparticle. In each case, we're going to want these massive vertices to have the same anti-symmetry property when we flip I and J. And we can do this by introducing this artificial generator that gets a minus sign when you do flip the indices. And we're at liberty to do this because anytime these graphs show up, we're going to address them with both a color factor and a kinematic numerator. So as long as we introduce this minus sign in both of these factors, then it doesn't matter for the amplitude. Now, we also want the massive amplitudes to obey color kinematics relations. And the first one is this one with two massive particles and two massless particles. And you can see that this is really just the commutation relation for this graphs. Now, additionally, if we treat our massive particles as adjoint type, we get this optional Jacobi-like relationship. And you see that this doesn't really work if we have particles charged in the fundamental, because then you'd start to mix particles and antiparticles. However, what we do find is that we can impose this optional Jacobi relation, and the resulting kinematic numerators can in fact be used to describe both adjoint type and fundamental type particle amplitudes. So just to sum up, we have these two parentheses 3 Jacobi relations that we're going to want our kinematic numerators to obey. And once we find something in a representation that obeys this, we can take the double copy. So meaning that we exchange the color factor for another kinematic numerator, and that's going to give us the gravity amplitude. And I'll get back to how we actually get this at the end. So now we can start with the actual bootstrapping method. And since it's a bootstrapping method, we start sort of at the lowest level, which in our case are the 3-point amplitudes. So we have two 3-point amplitudes, one that's massless and one with a massive line. Now each of these gets its own kinematic numerator function. And this function gets an ansatz. The ansatz just consists of whatever kinematic information we have here in a minimal basis. So you see we've got some momenta here, and we've also got the polarization vectors of the external particles. And similarly, the massive particle also gets this type of ansatz. Now, just by imposing these anti-symmetry relations that I mentioned, so for example, if we flip particles 1 and 2, we want this whole expression to get a minus sign. And by imposing this, these numerators are actually determined up to an overall factor. And then this factor we could set to the coupling, or we could set it to 1 just for simplicity in this case. So now that we have the 3-point amplitudes, we can start to build our way up to higher multiplicity. And we'll start with a 4-point amplitude with two massive scalars of distinct mass, as you can see from the distinct colors. Now we're only dealing with cubic topologies, so this is the only topology that contributes to this amplitude. So this amplitude gets this kinematic numerator, and you see in this case, there are no external gluons, so this is just a linear combination of momentum products. Now, we can impose the same type of anti-symmetry relations here because we imposed this anti-symmetry of the t's, and that actually determines this numerator up to some overall constant. And this overall constant we fix on factorization by sewing together these 3-point amplitudes that we found in the previous slide, and thereby constraining what this coefficient is going to be. So we get that the 4-point amplitude is this expression. And of course, this is just the propagator of this graph. So now we move on to an example that's a little bit more interesting color kinematics wise, because we have 2 topologies. And we distinguish them by the one that has a massive propagator that I'm just going to call NM, and the one that has a massless propagator, NM bar. Now, as you might remember, there is a color kinematics relationship between these graphs that we can write in this way. And as you can see, this actually shows us that we can write the massless propagator guy as a linear combination of the massive propagator guys, where we've just flipped around the arguments of these functions. And what this means is that we only need to give an ansatz to this massive guy, and then the information from this guy is going to get propagated back to the massless guy. So we give an ansatz to the massive guy. And in this case, you can see again that there are polarization vectors and momentum. And we constrain these parameters by imposing the anti-symmetries of both topologies and all the different Jacobi relations that we can write down. And then we fix the final coefficients on factorization of both graphs. So we find that the kinematic numerator of this graph is given by this expression. And again, the kinematic numerator of the massless guy, so this guy, is just a linear combination of these guys where you flip A and B. So we can continue in this way, and we see that we get this kind of pyramid scheme of amplitudes where we start out with the 3-point amplitudes that are determined by anti-symmetry, and then we can propagate information from these down into higher multiplicity amplitudes using factorization. And we've done this up to 6-point, and we could, of course, keep going to higher multiplicity, but our goal was eventually to get to loop level, so that's where we'll go now. So the bootstrapping method is very similar at loop level, and we can start with the 4.1 loop amplitude that has these topologies contributing. So we want to try to write this in terms of a smaller set of basis graphs as we did for the previous tree amplitude. But what does it mean to use color kinematics relations at loop level? We can look at the box graph as an example. So if we take a look at this propagator, you can think of it as a T channel or an S channel, depending on which way you flip it. In each case, you can change the connectivity, and you get this kind of relationship between these 3 graphs. Now, if we clean this up a little, we see that we can actually write the triangle as a linear combination of boxes. So we see that the boxes in this particular case are the basis graphs. Now, if we look at this other propagator of the triangle, we can do a similar thing. And that gives us a similar relationship where we see that the bubble is written as a linear combination of triangles, which are again written in terms of boxes. So if we write down all these relationships that we can find, we see that these 6 topologies can be described in terms of these 2 basis graphs. So we give these 2 basis graphs Ansätze, which in this case are a little bit more complicated because now we also have to put the loop momentum into the Ansätze. And then we fix, again, a lot of the coefficients on anti-symmetries and every Jacobi relation that we can write down. And then we fix the final physically relevant coefficients on 2 particle cuts. And here you see that we have 3 types of 2 particle cuts. We have a 2 massless particle cut, 2 massive particle cuts with distinct masses crossing, and then we have a 2 massive particle cut with same mass particles crossing. And now remember that we're still in the gauge theory, so these are ordered cuts that we're doing. But we have to determine what it means to do an ordered cut. So we look at this last guy, and we look at the left tree amplitude here. And what it means to do an ordered cut is on this side, we would have an ordered tree amplitude contributing. But what we mean by that depends on whether we treat it as an adjoint or a fundamental type particle. So if this is an adjoint type tree amplitude or cut, we get a contribution both from the S channel and from the T channel. And here you see the numerators of the S and T over the propagators. However, if we treat this as a fundamental type cut, these two graphs actually have different color factors. So they're different ordered tree amplitudes. In addition, you might remember that if we treat these particles as adjoint, we have this optional additional Jacobi type relation. And what we find is that we can impose these adjoint type cuts and these adjoint type color kinematics relations, and the resulting kinematic numerators obey the fundamental type cuts in addition to the adjoint type cuts. So as you can see, the adjoint type cuts are really combinations of the fundamental type cuts. So because of this, we choose to do the adjoint type cuts because there are just fewer of them. And we also looked at a 5-point amplitude, which encodes the first correction to radiation. And already here, we've only gone from 4 to 5 point, but in this case, things get a lot more complicated. For one thing, we now have an external gluon, so we've got a polarization vector showing up in our ansatz. In addition, the number of topologies that contribute to this amplitude are 33. And we're not including any tadpole diagrams here. Oh, and we weren't including any in the 4-point either. I forgot to mention that. And writing down all these types of color kinematics relationships that we did for the 4-point amplitude, we see that we can write this in terms of just 6 basis graphs. And to really give you an idea of how much work this is saving us from, if we were to give each of these 33 topologies its own ansatz, and remember that the ansatz is already in a minimal kinematic basis, we would start out with over 10,000 parameters to fix. And just by relating these graphs to each other, we've narrowed it down to just 2,000 parameters that we have to fix. So we fix a lot of these, again, on anti-symmetry and color kinematics relations, and we fix the final physically relevant coefficients on 2 particle cuts again. And you see that it's quite similar to the 4-point case. We have this new type of cut where we've got 1 massless and 1 massive particle cut. And in this case, we have 2 cuts where we have to decide what we mean by a color ordered amplitude. And just as at 4-point, we find that we can fix these numerators on adjoint type cuts with the, I'll call it the adjoint type Jacobi relation, and they satisfy both fundamental and adjoint type cuts. So what we find is that we can add this 1 loop layer to our pyramid of amplitudes. So we start out with the 3-point amplitudes, we propagate information from these down to higher multiplicities using factorization. And then we can propagate information from these again to the 1 loop amplitudes using unitarity cuts. So, sorry. Now that we have amplitude representations that satisfy the color kinematics duality, we can find the gravitational amplitude. But we're not just finding Einstein-Hilbert gravity where we only have a graviton. We also have a massless scalar and an anti-symmetric tensor running around here. And luckily, there are a few ways that we can get rid of these extra state contributions. So at tree level, if we only have a single massive particle, we can lock the polarization of these external states. So these are the 2 polarizations coming from the 2 copies of the gluons. And if we send that to the symmetric tensor, then this gets locked as a graviton. And if we do that for all the external states, the internal states are also locked to be gravitons. However, even at tree level, if we have 2 massive particles, these unwanted massless states can propagate between these massive states. But we can get rid of these using a physical state projector that only allows gravitons to flow through factorizations or unitarity cuts. And now it's an interesting question whether there's a double copy approach to this, either a way to get directly to pure gravity amplitudes or a way to double copy to these extra states and then subtract them. And Johansson and Acharov did this at loop level for massless external particles, where they added this kind of ghostly fermionic matter that with a negative sign that takes care of removing contributions from these extra states. And at tree level for massive particles, Luna, Nicholson, O'Connell, and White found a similar ghostly scalar that they also add with the negative sign that gets rid of these states. I think that was for 4 point and 5 point. And now we don't know what these generic double copy rules are going to be at loop level. So it'd be nice to gather some data to see what these rules should be. And luckily, there is a constructive approach to find at least what these contributions look like. And it's what we've chosen to call projective double copy. So this is a combination of the double copy and the method of maximal cuts, where we double copy the numerator of each graph, and then we use the method of maximal cuts to remove any extra state contributions.
Ingrid, do you have 5 minutes more and then questions?
Okay, perfect. Right, and this becomes a kind of bootstrappy approach because we can fix the external states of the 3-point amplitudes, so we can sort of bootstrap our way up from that. So we can look at some examples of this method at tree level, and here you see the 4 and 5 point amplitudes with 1 or less massive scalars. And these are the n equals 0 supergravity numerators, which is what we're calling this gravity with the extra states. And here you can see contributions from extra states. And just as I mentioned, we see that there are no contributions from these other states for these amplitudes. However, when we add the extra massive particle, we see that there are indeed contributions from these extra states. So the way our method works is that we just subtract these contributions from the numerators of the graphs. And we've also looked at this at 6 points, and you can see that as we go up in multiplicity, these extra state contributions also get more complicated. But the method itself is very straightforward and systematic. So I'd like to just quickly go into the details of a simple example. So if we take the numerator of the 4-point amplitude with the 2 massive scalars, we see that the n equals 0 supergravity numerator is just the double copy of the gauge numerator. Now, we want to compare this to a factorization where we're only letting gravitons flow through. So we start by imposing cut conditions on this expression. And then we subtract this sewing together of the 3-point trees with a physical state projector with only gravitons. So what we have here is the contribution from all the states minus the contribution where only gravitons are allowed to propagate. So what we're left with is this extra state contribution. So then we can go back and subtract this from this numerator, and that gives you the graviton numerator. And another nice thing about this approach is that it gives us these kinds of difference numerators. So these are the types of things that we can look at. This is the difference numerator attributed to this graph. So this is the type of thing we can look at to see what a ghostly particle might look like for these types of amplitudes. Now, we can also do this at loop level relatively easily. And here you see the maximal cuts of the relevant topologies at 5 point. And we start by just taking all the maximal cuts of all these topologies and then comparing them to the unitarity cuts with the physical state projector. And again, any extra state contribution you would get for one of these topologies, you just subtract from this numerator. Right, and since a maximal cut only has a single topology contributing, this is information that's sort of inherent to this topology. And once we've done that for all the maximal cuts, we can move over to the next to maximal cuts, where we release the cut conditions on one of these propagators. And you see that if we get extra state contributions from a cut like this, we can subtract it from one of the topologies that contributes to this type of cut. And similarly, we continue with the next to maximal cuts and the next to maximal cuts. So what we end up with is a set of numerators that give us the graviton amplitudes. And this might seem like a lot of work, but it's actually very systematic and straightforward and easy to automate. So of course, the first interesting thing to look at for future work would be to look at these difference integrands that we have and see if there's a way to double copy directly to pure gravity. And we would also like to extend our representation to higher spin particles in both fundamental and adjoint representations. And of course, use these results that we have to generate some classical observables like radiation, for example, and eventually to extend to higher loop order. So just to summarize, we did find a representation that satisfies the color kinematics duality at both tree level and loop level. And these numerators are completely determined by color kinematics and their factorization and unitarity properties. And these representations that we find can be used to represent massive scalars that are both fundamental and adjoint charged. So thank you.
Thank you very much. It's a very interesting talk. Let's see if there's any questions. Yeah, there's a question from Gustav.
Hi, can you hear me?
Yes.
Yes.
I'm just curious whether, so obviously people, Henrik and Alex notably, have looked at the idea of using ghosts to subtract off these unwanted states in the amplitudes. I'm just wondering whether you guys tried that, and if so, what the result of that was, if anything came of that.
So it's definitely, I'm careful about calling them ghosts. I've been told to call them ghostly matter. And it's definitely something that we've started looking at, because once you start producing these sort of different expressions, maybe I can go back to, I think, the 6 point here, then you can start to see if there's some way of squaring these expressions. And it's definitely something that we're working on at loop level, but we haven't completely nailed down what the different rules are going to be. But yeah, it's absolutely something that we're looking at.
I mean, because I guess the dream would be that if you could include something in the gauge theory, which would essentially automatically cancel these states, then there'd be no need for a projection anymore.
Yes, exactly. That would be very nice.
Okay, thanks.
All right, so next question is by Gilbert.
Yeah, thank you for a very nice talk, Ingrid. So I just have a very simple question. So have you tried to take the classical limit of these amplitudes? And would you encounter, these problems that one encounters at tree level, for instance, the super classical terms showing up that in the end they cancel away from when you sum up all of the contributions?
Yes, so we have tried to take the classical limit. So we've started actually to look at the classical Yang-Mills contributions. And we've tried to reproduce the 4.1 loop calculation in, I don't remember the paper by Donald and friends. And of course, we do get the same type of superclassical terms, but they do cancel against the cuts in a similar way. So now we're looking at the same thing at 5 point, whether there are enough cuts that could get rid of the superclassical terms that show up there too.
I see. But so, for instance, also say if you think of just at the tree level, right?
Mm-hmm.
Like the usual PCJ representation of the, say, the 5 point amplitude.
Mm-hmm.
Gives you, super classical terms if you consider like individual terms, which cancel away. So you could, for instance, find a gauge in which these super classical terms do not show up at all. Like I'm just wondering where in this sort of representation you could, not have those at all, say at tree level.
So if there's if this is a representation where they don't show up graph by graph even.
Yes.
I'm actually not sure. I know that we reproduced the 5 point and we got rid of the classical terms in the end, but I'm not sure whether that was from summing together the graphs or whether they just didn't show up at all. So, but that's an easy thing to check, and I can get back to you if you want.
Okay, thank you.
Sorry, I was muted. There's one more question, so let's do that quickly before we end. All right, Alex.
Hello, thanks for the nice talk. So I just wanted to make sure that I understand your approach to subtracting those states. So in the normal double copy, fit the cuts on the gauge theory side, and the double copy guarantees that the gravity cuts will be satisfied. And it seems like in your approach, you use the double copy and get the gravity plus or n equals 0 supergravity, and then you on top of that also have to cook up cuts for the additional contributions, right? Is that the case?
So that is the case for this projective double copy method. That's exactly what you described now.
Mm-hmm.
So of course, if you could add something in the gauge theory, like you mentioned, then you wouldn't have to do these cuts at the end. But this is a nice way, since we don't know what these terms that we could double copy would be at loop level. This is a nice way to just collect the data and just see what the states look like. And then you could try to guess your way to what type of terms you should be adding to the gauge theory. Right.
But in some sense, you still have to go through the cuts in gravity. So I guess the question is, would it make sense? Well, how much do you gain from not going to gravity directly? But you pass through the gauge theory cuts, and then you still do cuts in gravity. So my answer would be that probably you gain from organizing your integrand in a double copy like fashion. But what do you think about what you gain by this method?
Do you mean compared to just doing the gravity cuts, or?
Yeah, just doing pure gravity cuts.
Well, I think if you just did the gravity cuts, you wouldn't really get the difference, would you?
Well,
and you would just get the gravity contributions?
Yeah, you would just get the gravity contributions from the start. But you would have, I guess you would have to ansatz each topology, right?
Yeah, I think so.
Yeah, so.
So I guess maybe that's a different way to go about it, is if you ansatz each gravity topology and then just do the gravity cuts, then maybe you would end up at the same thing. But in this case, in a way, though it seems more cumbersome here, but in a way you start out with a much smaller ansatz.
Yeah, okay. That's what I thought. Thanks.
Great, thank you. I think that's it. And then now we have a half an hour break, but let's thank Ingrid for her talk and all the speakers of this morning or afternoon session.
Thank you.
Right, so in half an hour,